The next three lectures from 34 to 36 are about alcohols, phenols, thiols, and ethers. So as usual, I've divided them in two parts. So the structure of alcohols and its physical properties are up next. So alcohol is an organic compound that contains a hydroxyl group and an alkyl group. So two groups has to be there, hydroxyl group which is attached to the alkyl group, and it must be an organic compound. Such a compound will be known as alcohol, and the general formula is ROH, where R is the alkyl group. It can be a methyl group, ethyl group, propyl group, any alkyl group can be there attached with the hydroxyl group, that is OH. Next are physical properties of these alcohols, and the molecule of an alcohol is very similar to water. So this ROH, which represents the alcohol, the structural similarity is there between it and the water. Hydroxyl group is a very polar molecule and therefore it can make hydrogen bonds readily. An important thing to remember is that these alcohols have got high boiling points relative to their molar masses, and this high boiling point is mainly due to the formation of hydrogen bonds that these alcohols can make. So on the right side we have an alcohol, and on the left side we have a comparable hydrocarbon, which is a simple butane 4 carbon molecule. On the right side we have propyl alcohol, and both have relatively same molar masses. The number of atoms are almost similar, but you can see the difference of boiling point is huge. The alcohol has got very high boiling point, 97.2 degrees Celsius, whereas this simple hydrocarbon has got minus 0.5. These alcohols, as we said, have got higher boiling points than the comparable hydrocarbons because of the hydrogen bond present between them, and the alcohols are also soluble in water. Also the same reason, because they can make hydrogen bonding between the alcohol and the water molecules. Here we have a table of alcohol and showing their boiling points and the solubility in water. And the general rule is that in a homologous series, as the molecular weight increases, the boiling point of these alcohol increases, but the solubility in water decreases. So as we go from top to bottom in this table, the molecular weight is increasing. We are getting the bigger alcohols, as we can see in the formulas as well. More number of carbons are there. Methanol has only one carbon, or the methyl group attached with the OH. Ethanol has two, and then propanol 3, butanol, and so on. So going from top to bottom, we are increasing in molecular weight, and we can see that this boiling point is also increasing as we do go down. The smallest one has 65 degrees Celsius, whereas this one hexanol has 155.8 degrees Celsius higher boiling point. And when we go down the table, we can see that solubility is decreasing. The top three, which are small, are completely miscible, or you can say completely soluble in water, and the remaining ones, the bigger ones, keep on decreasing their solubility in water. So we can see these two properties clearly in this table. Next are the classification of alcohols. So it's a diverse group. How can we basically classify them or group them in different groups? So here we have an example, methyl group, which is the smallest of these alcohols, CH3, which is the methyl group attached with the hydroxyl group. And the central carbon of this methyl is known as carbinol carbon. So that is one important thing to remember. Then comes the 1 degree, which is represented by primary alcohol. So these primary alcohols, the carbinol carbon is attached with another R group, or one R group is attached with the carbinol carbon. In secondary alcohols, or as represented here, 2 degrees alcohols, the central carbinol carbon has got two R groups, and in tertiary alcohol it has got the three R groups, replacing the hydrogen atoms that we saw here in the methyl alcohol. So this methyl alcohol is simply words, or more commonly known as methanol. An example of this primary alcohol is ethanol, and for the tertiary alcohol it's 2-propanol, and for secondary and tertiary alcohol example is 2-methyl 2-propanol. So these are a few examples that you must memorize for the alcohol classification. Next is the nomenclature, or naming of these alcohols, and we have the same system, which is standard organization in chemistry, known as IUPAC, and it has got a few rules for naming these alcohols as well, just like we have done some rules for some other chemical compounds on the by the same organization, that is IUPAC. So first up, or first rule will be that the name will be based on the longest chain that contain the OH carbon, basically, or the carbon that is attaching the OH group. So the longest chain is going to be taken, just like alkyl groups, or alkanes, alkenes, and alkynes. Similar thing, always for the hydrocarbons we usually take the longest chain, and that chain must have the carbon that is attaching the OH group. Once we have it, the end letter E must be replaced by OL. Say for example it is methane, we will replace the E and convert it, or replace it with OL, so we will call it methanol. Similarly, for ethane it will become ethanol, for propane will become propanol, and so on. Then the chain will be numbered for carbons. Obviously we have to number the carbons 1, 2, 3, 4, and the numbering of the chain will be from the end that will be closest to the OH carbon. So the carbon that is attaching the OH group, that will get the lower number. We will start from that, and the name will be prefixed with the number indicating position of the OH group. So the carbon that is attaching the OH group, we will have to prefix that number before the name of the alcohol. And the last rule is for cyclic alcohols, that is ring-like structures, OH will always be at the carbon number 1. So whichever carbon has the OH group, we will number it 1. So here we have an example of this naming of the alcohol. And first up we have to name the parent compound. Find the longest chain as usual. So this one is the longest chain, and the rule was it must have the carbon that is attaching the OH group. So this OH group is attached with this carbon. This carbon must be a part of the parent chain, and this has got 4 carbons in it. We can count them, therefore it will be called butane. Because there is this OH group and it is an alcohol, so we replace the E with OL, and instead of butane we call it butanol. Next thing is numbering of the carbon that is attaching the OH group. Sorry, even before that we will have to check which carbon to start numbering with, and if we start from this and left to right, then the carbon that is attaching OH will be at carbon number 3. If we say 1, 2, and 3, this will have the third carbon which attaches the hydroxyl group. But in the last slide we just saw that we have to start from the end where the carbon which is attaching the OH group has the lowest number. So we will have to go from right to left, and this carbon which is attaching the hydroxyl group will be carbon number 2. We have to write this 2 as a prefix to the name that we just find out was butanol. So we will call it 2-butanol, as we can see here. So number the parent chain to minimize the number of carbons. In other words, or simplest words, we have to start with the N, which has the carbon attached with hydroxyl, the lower number. So applying this rule, we will number from left to right, right to left, as we have done here, 1, 2, 3, 4, going from right to left. And the last part is if there is a branch or a group present, substituent present, we will have to write its name and the carbon that is attaching it. So it will become 3-methyl 2-butanol because it has got a methyl group attached with third carbon. It has got the hydroxyl group which is making it an alcohol attached at carbon 2, so 2-butanol it is. Next we have a few more examples and the IUPAC names of these alcohols. And to begin with, we have got a 2-carbon molecule that is attached with the OH. So 2-carbon is ethane, and because the hydroxyl group is attached, so we replace the last E with the with the OL, and this will become ethanol. We don't have to write the positioning of the OH because it will always be, there are only 2 carbons in it, so it will be with the first carbon always. And it's also called as ethyl alcohol in common names. So next we have this big molecule which is pentanol, as we can count the carbons of the parent chain, 1, 2, this one 3 right besides it, 4, and the 5th one. So this one has got the hydroxyl group at carbon number 2, so we call it 2-pentanol, and the methyl group is also attached with carbon 2, so it comes before that 2-methyl 2-pentanol it becomes. Next we have a 1, 2, 3, 4, 5, and 6 carbon molecules. It's a hexanol attached with carbon number 2, so simply write the number and it becomes 2-hexanol. And the last one we have a pentanol which has got a bromine substituent attached with it. So this is the parent chain, 1, 2, 3, 4, 5. So it's a pentanol, hydroxyl at carbon number 2, it becomes 2-pentanol, bromine at carbon 3, so 3-bromo 2-pentanol is the full name. Another similar example, guys, for the IUPAC names, but this kind of example can cause a little bit of confusion. So we have got this molecule, and if the numbering is not there, then obviously there will be the problem. So we find the longest chain, and we can see if we go in this direction, this is the longest chain. It will have 1, 2, 3, 4, 5, 6, 7, and 8 carbons in it. But the problem with this one is that we have to find the longest chain with the OH group or the hydroxyl group carbon. This carbon which is attaching the hydroxyl group must be a part of the chain. If we take this chain, then this carbon will not be a part of it. So the blue chain is longer, or the one that I've just represented, but it does not have the OH group. So we will have to go by the red numbering, which in which has the carbon which is attaching the hydroxyl group. So we number it basically uh, in this way: 1, 2, 3, 4, 5, and 6. So it becomes hexanol, and carbon number 1 in this case is attaching the hydroxyl, so it becomes 1-hexanol. Now this whole thing will be the branch that is attached at carbon number 2. It's a 3-carbon alkane, so it is 2-propyl 1-hexanol. Next we have the IUPAC naming for the cyclic alcohols, and again we have some rules. Most of the same rules will apply for the general hydrocarbons. with a little bit of differences. So name the parent compound, which in this case or most commonly is the 6 carbon ring. So 6 carbon hydrocarbon is known as cyclohexane. So we will call it cyclohexane, but because it is an alcohol, has a OH group, so this last E will be replaced with OL and it becomes cyclohexanol. Next thing is that we read earlier as well. In a cyclic compound, the carbon that is attaching the OH group will always be numbered 1. So we go towards the substituent or do the counterclockwise numbering. So this carbon which is attaching the methyl group here becomes carbon number 3. So we write it 3-methyl cyclohexanol. We don't have to write the number of this hydroxyl group, so we will not call it 1-hexanol because it is always going to be at number or position 1. So OH must be at carbon number 1 always. So the IUPAC name for this compound is 3-methyl cyclohexanol. Again, more examples for cyclic molecules. So first up, we again have a 6 carbon cyclic structure, which is hexane. Because it is an alcohol, we can see, so it will be called cyclohexanol. And we can write 1, but most of the time it's not written, as is the case here. So simply cyclohexanol is correct as well. Now at carbon number 2 and at carbon number 3, we can see a bond that is present here. Now what does that bond mean? That there is a carbon present at this end of the bond, as we don't have to write the carbons all the time. This simply bond represents that this carbon, which is also not represented, is bonded with another carbon. Now when there is a lone carbon here, we will always have to fill up the hydrogens. So because this carbon is making one bond here, it must have 3 other bonds present, and all of these will be filled up with hydrogens, as the hydrocarbon is the molecule. So the 3 bonds will be filled up with hydrogen, and this will become a CH3 group. So we can simply write it as a CH3 group here as well. CH3 is a methyl group, both are the same. One at carbon 2 and one at carbon 3, so it becomes 2,3 dimethyl cyclohexanol or 1-cyclohexanol. Both terms are correct, but as I said, this one is more commonly used. So methyl group at 2,3 positions, so we write it dimethyl. Next up, again we have a cyclohexanol, and the carbon attaching with the hydroxyl group will be at carbon number 1. Always we go counterclockwise. Position 3 has got a ethyl group this time. You can see a bend here, and the bend means that there is a carbon present here, and this carbon will always fill up the hydrogens, which will be 2 in this case. So it's a CH2 basically, not written. So the CH2 and CH3 is the ethyl group. So 3-ethyl, and here we have a simple methyl group. So 5-methyl and 1-hexanol. I hope you have got the difference between the two. If it's a straight bond, it means that this is simply a methyl group, like in this case as well. Even if it is nothing written here, you must have to understand that the methyl group is present, a carbon is present, and it will always be filled up with the 3 hydrogens. Now when a bend is there, this bend represents a carbon as well, and that will also fill up the hydrogen. So this whole branch that is attached with carbon number 3 is this one, which I've just circled, CH2CH3, which is a ethyl group. Next up is the simple molecule cyclohexanol. Nothing significant about this one. Carbon number 1, it is always to remember. As I said, we don't have to write it down always. And if it has got alternate double bonds, then it's a very common molecule. I think that went by before as well. This will be known as phenol. Now, some of the alcohols have got some common names as well. These are some historic names at times, old names that take their place in the IUPAC system. So these are not IUPAC names, but commonly used names of some alcohols. And for these common names, basically, we first write down the alkyl group name and specify if it's a special type, like in this case it's butyl, and then we write the word alcohol. So it has got 4 carbons, so it's the molecule is called T-butyl, and alcohol at the end of it. Similarly, this one, 3 carbons, isopropyl alcohol. Next up, we have a few examples. In the first part, you have to name these molecules or these alcohols by the IUPAC system. So these are a few examples that you got to do it by yourself. Second one, you have to write the structural formula. So make the structural formula for these compounds. So I will go through a couple of these. So first up, we have a 2 carbon molecule with a chlorine atom attached with it, and it's an alcohol as the OH group is attached with it. So we can simply call it ethanol because it's a 2 carbon alcohol, but with the chlorine we will have to call it chloroethanol, or 2-chloroethanol to be specific, because this chlorine, this carbon will become carbon number 2, and the one that is attaching the hydroxyl group will be carbon number 1. Similarly, this 5 carbon molecule which has got the hydroxyl group, so it's an alcohol. So 5 carbon ring structure is cyclopentane. If it's an alkane, if it's an alcohol, we will call it cyclopentanol. Similarly, simple structures, guys, you can do it by yourself. 3-bromopropanol. Propanol means it's a 3 carbon alcohol, and there is a bromine atom Br attached at carbon number 3. Now, some of these alcohols are very important medically in the hospital settings. They are commonly used, and the smallest of these is the methanol, which is just a CH3 attached with the OH. So a methane with the OH is the smallest of the alcohol, methanol. So it's colorless and odorless liquid, doesn't have any color, doesn't have any smell, used as a solvent to dissolve other substances. It is very toxic, like a poison, and can cause blindness and even death if it is ingested or drank, and it can be used as a fuel for energy purposes. Second one is ethanol. So the 2 carbon alcohol that is uh, right here at the bottom, 2 carbons, ethane attached with the OH group. So that is what we call ethanol, or commonly called as ethyl alcohol. So this is the common alcohol that you guys might be familiar with the name, that is used commonly in the Western world. So again, it's a colorless and odorless liquid, doesn't have a color and doesn't have a smell. Widely used as a solvent as well, just like methanol, and it is the alcohol in the alcoholic beverages, the drinks that are taken commonly in the non-Muslims. So derived from fermentation of carbohydrates. There is a process known as fermentation. Many reactions are involved, and these carbohydrates can be converted into this ethanol. And the beverages that are produced, the drinks that are made from it, will vary, because, in other words, it will be different from each other depending upon the starting material and the fermentation process. So the most typical way in which it is produced is from the sugar glucose, C6H12O6. As I said, several steps will be there, several reactions, and enzyme is also usually present to convert it into ethanol. This process is called fermentation. Next is 2-propanol, or also called as the common name isopropyl alcohol. So this is the 3-carbon alcohol hydroxyl group is attached at carbon number 2. Colorless, but it has a slight odor, so slight smell is present. Commonly known as rubbing alcohol as well, so it's got another common name. Again, poison or toxic when ingested, just like the methanol, and it is used in various ways. It is as a disinfectant used, uh, it can be used as a disinfectant. In other words, to clean the wounds up, or that kind of medical purposes is done by propanol. It's also used as a astringent and also industrial solvent. So just like the previous two alcohols, this one is also a good solvent for dissolving other materials in it. Next up is an alcohol known as 1,2-ethane diol, or the common name ethylene glycol. So this one is a little bit different because it has got two hydroxyl groups. It is two carbon molecule like an ethane, but has two hydroxyl groups instead of one. Therefore, the name 1,2-ethane diol. And its most common use is in the automobiles or in the cars, you can say, used as antifreeze. Has got a sweet taste, but it is extremely poisonous to remember. And when it is added to water, it will lower the freezing point of water, but it will increase the boiling point. So when it's mixed with water, it changes the properties of water. Next up are reactions involving alcohol. So first up is the reaction in which alcohol will be as a product. So we can call it preparation of alcohol. And the reaction is hydration, which is simply addition of water to the carbon-carbon double bond of an alkene. So addition of water to the alkene will produce an alcohol, and it will require a very small amount of an acid as a catalyst. And we can see an alkene with a double bond between the carbon. I think these reactions were there before in some previous lecture as well. Anyways, adding water to this alkene will remove the double bond and convert it into a single bond, and the H and OH will be added to one carbon each. And when this hydroxyl group is attached, this will be converted into an alcohol. Next up is hydrogenation, and which is addition of water. So addition of water to the carbon oxygen double bond of an aldehyde or a ketone also produces an alcohol. It's a type of addition reaction, and considered to be a reduction reaction, which is the loss of electrons. Again requires a catalyst, which will be in the form of platinum, palladium, or nickel. So any of these three metals can be used as a catalyst. So an aldehyde or ketone which has a carbon double bonded with the oxygen, we will add a hydrogen molecule to it, and it will be converted into an alcohol. Next up is the reversal of the hydration reaction that we just saw to produce alcohol. This one is dehydration of alcohol. Like hydration was adding up the water molecule. Dehydration is removal of the water molecule from the alcohol. And this can be done with the heat in the presence of a strong acid, and the product will be an alkene this time. So it's more or less the reversal of the reaction that we just saw, in which we added water and alkene to produce alcohol. In this one, we are removing water from the alcohol. So dehydration is the type of reaction which is known as elimination. And in elimination reactions, the molecule loses atoms or ions from its structure, and what is being lost is water in this case, in the form of OH and H, which are removed from the adjacent carbon atoms to produce the alkene, and these H and OH join together to make the other product, which is the water. And a reversal of the hydration reaction, as I just talked about, that forms the alcohol. So heating up the alcohol in the presence of a strong acid will reverse the process, will give us an alkene and the water molecule. Next up is something that we call the Z-Seb's rule for this elimination reaction that we just saw. So some alcohols, especially the bigger alcohols, when dehydration reactions will take place, they will produce a mixture of products. So we can have 2 or 3 different products basically. As we can see here, we have the 2-butanol, which has got 4 carbons in total. When the dehydration reactions takes place, water will always be formed, but we can get 2 different products. So that is 2-butene, where the double bond is present between carbon 2 and carbon 3, and also we can there is at least a possibility of having 1-butene, in which the double bond will be between carbon 1 and carbon 2. Now Zetsev's rule states that during such multiple products or mixture of the products during an elimination reaction, the alkene with the greatest number of alkyl groups on the double bond or the double bonded carbon will be the major product. When there are 2 possibilities, as in this case, one will be the major product that will be formed most of the time, and one that will be the minor product that will be formed less times than the major product, just like the Markovnikov's rule that we studied earlier as well. Just for the sake of convenience, we can say this major product will be formed 80% of the time and minor product will be formed 20% of the time, so that we can understand it a little bit better. Now 80% of the time, or the major product, you can say, will be the one in which the alkene with the greatest number of alkyl groups on the double bond. This is the key words to remember. Greater number or more number of alkyl groups on the double bond. So here we can see the double bond between these 2 carbons, 2 and 3, and we have 1 alkyl group here and 1 alkyl group here. So this one has a total of 2 alkyl groups between the carbons that are making the double bond. Whereas in 1-butene, here is the double bond. This one does not have any alkyl group. This one has got 1 alkyl group, which in this case is a bigger one, that is the ethyl group. So this one only has 1 alkyl group, whereas in this case we have 2 alkyl groups, 1 here and 1 here. That is why this one is known as the major product. Next up is a similar example where we have to predict the product of dehydration, or you can say the major and the minor products. So we have 3-methyl 2-butanol, and when it is heated in the presence of an acid, we can get 2 products. So one is 2-methyl 2-butene plus water, the second product, and 3-methyl 1-butene. The double bond again can be present between carbon 2 and carbon 3, or it can be present between carbon 1 and carbon 2. So same is the case exactly like the previous example. In this scenario, the top one, here is the double bond between this carbon and this carbon. So we'll have to check these carbons have how many alkyl groups. So this one has got 1 over here methyl group, and this carbon has 2 more methyl groups, 1 here and 1 here. So the total number of alkyl groups in this case becomes 3, and whereas in this one, here is the double bond between these 2 carbons. The carbon on the right, this one does not have any alkyl group attached to it, whereas the left one has got 1 alkyl group, which is in this case is the big one, where that is the propyl group, but it's only 1. Therefore this is the minor product and this is the major product with more number of alkyl groups attached at double bonds.